Hello everyone, I am Dr. Faizi. Today in this video, we are going to learn about pyrazole. So let us start learning of pyrazoles. You can see here the properties. First, aromaticity. This is the structure of pyrazoles. So there are two nitrogen here, one NH, one N. So this nitrogen is pyridine-like and this is the pyrrole-like. What does it mean? Why we are focusing here pyrrole and pyridine? Because they are opposite in properties. We will learn later on. So this is the complete structure of pyridine and this is the complete structure of pyrrole. So if you draw this structure, it will look like this. This nitrogen have lone pair of electron and this nitrogen sp2 hybridized orbital and unhybridized p orbital. So this is the molecular orbital of pyrazoles. Now this is some important properties. Pyrazoles have 3 carbon, 2 nitrogen. You can check it. sp2 hybridization is planar. It makes a planar pyrazole ring structure. Next important point, for this point is important for you for objective exams, objective questions. Each ring atom also contains unhybridized p orbital and that perpendicular to the plane of sigma bond. Already you have seen. P orbital are parallel to each other. So overlapping between orbital is possible. The total number of non-bonding electrons are 6, 3 of 3 carbon and 1 from one nitrogen and 2 of the other nitrogen. Now the resonance of 6 electron follows the Haeckel. So pyrazole is aromatic. Now properties. You see the tautomerism. You already know the meaning of tautomerism. So rapid migration of hydrogen from one nitrogen to other. Look at here, 3,5-methyl pyrazoles. 3,5-methyl pyrazoles. Why? Here most important things you have to focus on the 3 and 5 positions, and that is the need for the heterocyclic chemistry. So you know the NH will got the 1 position, then another nitrogen 3 position methyl. Again in the second structure you can look at here. This is 1 and this is 2 and this 3, 4, 5. Just remember it. Hydrogen bonding, you can see this intermolecular hydrogen bonding, intermolecular hydrogen bonding. Now synthesis is very important from pyrimidine. You know this 6-member ring and the situation is like that. This is known as pyrimidine. So pyrimidine is very susceptible to nucleophilic additions. It reacts with hot hydrazine solution to give pyrazoles. So this is one method of preparation of pyrazoles. Now the mechanisms. Look at here. Mechanism follow addition of nucleophile ring opening. Nucleophile ring opening, ring closures. First focus on addition of nucleophile. Nucleophile ka addition with ring opening and ring closing sequence. Look at the step first, nucleophilic addition, formation of nitrogen carbon bond, and then ring opening, then ring closing, and then you will get the pyrazole. Now friends, another synthesis, norpyrazole synthesis. Norpyrazole synthesis. Norpyrazole synthesis, this reaction convert a hydrazine or its derivatives and a 1,3-dicarbonyl compound to a pyrazole using an acid catalyze. Look at the reaction scheme. This is the structure of 1,3-dicarbonyl compound and you know the hydrazines, and this is your product pyrazoles. Now again go through the mechanisms step by steps. You can see the lone pair approaching the acidic medium and forming OH plus. Here carbon oxygen double bond, and then hydrogen approaching the carbon center of C double bond O, and then formation of carbon nitrogen bond, then shifting of positive charge on nitrogen. Then you can see the arrangement of H from nitrogen to oxygens, and then you can see the formations of imine, and then in acidic medium it is taking the OH plus, then nitrogen carbon formation and cyclization occurs, then shifting of protons forming OH to again removing of water, and then trapping of H plus, and after rearrangement you will get the pyrazoles. So write it down in your notebook. In tomorrow class we will discuss this point also. So you can see the non-pyrazole synthesis, another example, unsymmetrical dicarbonyl compound. You will get the isomeric mixture 1,5-dimethyl 3-phenyl hydrazole and 1,3-dimethyl 5-phenyl pyrazoles. Now from nitrilamine, pyrazoles are produced by a dipolar cycloaddition between alkyne with nitrilamine. Look at this reaction scheme. From diazo compounds you can also get the pyrazoles. Now electrophilic addition to nitrogen, protonation, it is showing the basic properties. The pyrazole except proton act as base. Look at here, and this is the beauty, the pyrazolium cation under resonance conditions. Now N alkylation, you can see methyl iodide, it gives the N-dimethyl pyrazolium salt. Now electrophilic addition to nitrogen, N-alkylation, pyrazole react with alkyl halide and first give N-alkyl pyrazolium salt, and this salt can lose an N proton in an equilibrium with unreacted pyrazoles generating N-alkyl pyrazoles. N-alkyl pyrazole react with the alkyl halide and gives N1N2 dialkyl pyrazolium salt, and the pyrazolium salt is look like salt and it is soluble in water. So electrophilic substitution to carbon. So pyrazole undergo electrophilic substitution at 4th positions. Now look at the position of 4th, where it is 4th position. Electrophilic attack at position with the intermediate. Now you can see the options, like you already know about the pyrrole, furan, thiophene reaction like this. So if electrophile attack and 3, what will happen? If electrophile attack and carbon 4, the situation is like that. When it attack on carbon 4th, then will attack. So what is the difference? Why carbon 4th is the favorable condition for the electrophilic substitution? So reason is here. Intermediate with positive azomethane N highly unfavorable. So the formation, if it attack on carbon 3 and carbon 5, so this situation will come which is not favorable. So carbon 4 is favorable in case of pyrazole. So the electrophile attack at carbon 3 and carbon 5 generate highly unstable positively charged azomethane intermediate. Electrophilic attack at carbon 4 complete without any such highly unstable intermediate. Thus transition state is much higher for carbon 3 and carbon 4 attack than carbon 3 and carbon 5 attack than carbon 4. Electrophilic attack takes place readily at neutral or alkaline media, as the pyrazole protonated pyrazole is more resistant to the electrophilic attack than pyrazole. This important point is for your objective questions. Now you can see the nitrations, halogenations, N-bromosuccinamide, NBS reactions, bromination. Now you can see the oxidations, reductions, you are getting a step-by-step product, 1-phenyl pyrazolidine and 1-phenyl 4,5-dihydropyrazole. So nomenclature is also very important because you have the target to synthesize pyrazoles, but whatever the reduced product you have to give the nomenclature reduction after reduction. Now ring opening, you know, the N substitution pyrazole reacted with a strong base sodamide cause ring opening. Look at the reactions, how deprotonations, then you can see the formation triple bond, breaking of nitrogen bond, and then acrylonitrile derivatives. So my friends, I hope this video will be helpful to you. A lot of medicinal uses, so I am not going to in medicinal uses because your examination is near. So focus on the synthesis, chemical properties, and some important logical questions, reasoning types, why it is happened, why not. So what is the positions of 4, why 3 and 5 is not comfortable for the electrophilic reaction. So such type of critical thinking you have to think about it. Thank you for watching.